Welcome to the latest Renaissance video. Today we're going to show the complete instructions of the 12-inch industrial motor kit here. So what we have here is it mostly assembled with a controller here and various parts. So let me bring the camera in closer here and so let's start off with some of the parts that we have. We're going to get into the electronics a little bit later, but here's the speed control board. And then here's what we call the opto board. So what we have several coils here, 3 of these, 18 gauge wire. I think we might go down to 12 gauge in the near future. I do have a 12 gauge rotor over here. Show. So this is the one we showed with the FET video. So we may switch to that. I think we're going to do FET control from now on. And then we have, let's see, the plate. So this is a stainless steel plate, and then these allow for the coil to be harnessed in the right location. And we have rubber, strong rubber around the coils so that they hold them in firmly and don't rub against any kind of metal. These also provide some ventilation, and as this rotor spins you can see that there's going to be some air movement, fan action there, as you can see here in the grooves. So what we have in here is we put these together for customers because it's very dangerous. These are 300 pounds pulling force each magnet in there, 2 by 1 by 4 inch magnets, and this is specially machined so that we can slide the magnets in the side, put an end cap in there. Then we also have on one of the hubs keyway, 1/4 inch keyway that goes on the shaft, corresponds right there. And then there's another keyway on the end, an optional keyway there. So let's begin with, see, everything's sticking to these magnets. To be very careful. So let's look at this hub here. This is the timing hub, and this has to be positioned according to the right time. And these are little timing tabs here. So this represents the off time. So the 3 coils, 2 of them are in phase and 1 of them is out of phase with the third one is out of phase. So we have 2 coils firing and 1 off and the other one firing. And so we have 2 of these optos positioned 180 degrees out from each other, while group 1, as we call them, so like 2, in this case 2 of the coils are group 2, and these ones are already set up for that. So when group 1 is firing, which represents the open area here, then group 2 is off. So in this case, group 2 is at the bottom. We'll see down in this one is group 1 is at the top. So there's 2 of these. And so they're 180 degrees apart from each other. So while group 1 is firing, group 2 is off, vice versa. And then what we have is the speed control will break up the off time, or the on time, sorry, and we'll pulse it. So we'll have a longer or shorter frequency and pulse as we adjust the pot. Well, there's 2 pots actually down here, so we'll get into that a little bit later on. So one's the pulse and one's the width. Pause. So we have to put our spacers in on the shaft, and then we position this and tighten it down once we've got this figured out where we're going to set it. So we can mount the shaft, or sorry, mount the rotor on the shaft and then adjust this where we want it. And what we do is just take a battery. First thing I want to do is show the motor inside. Let's bring this around this camera. So we have one of the coils is off to show inside and the timing. This timing has already been set. First of all, we want to know that this spacer will provide the right space between, so that the timing hub plates will end up being right in the center. You don't want it rubbing on either side of the space, the gap. So if you look in the center, there's a little LED transistor, opto transistor, photosensor, and then on the back you can see the numbers, or the letters A, K, C, E. So each tab represents that, and we've color coded. A is red, K is black, C is white, and E is green. So we have these wires that will come off of this, and there's 2 of them. So on the schematics here, you'll see the red wire A, black wire K, white wire C, green wire E. This represents the very basic circuit, and this represents the full schematic, in which we have 2 optos in series with each other, at least on the primary side. And then they're in parallel, semi-parallel. We'll go over that in a minute. So what we want to do is determine the timing. What we're trying to do is make sure that this rotates first of all, we have to decide what direction we want to turn it. This one I actually put sort of backwards because I really don't want my wires coming out on the same side that I'm running the load off of. So I have the keyway over here. Normally I would put it over there on the other side. Anyway, what we want to do is determine which way is turning right, which way is, or clockwise. So right now I've got all the wires, oops, of this one coil connected up. What we want to do is solder all of these together, not clamp it like this, because if you clamp it like this, there's going to be a couple wires that don't make proper connections. But for now, we're just going to show it this way. So I'm just going to connect. It doesn't really matter when we start what coil is group number 1 and which coils are group number 2. So we take a battery here, and one end we're going to decide with this particular coil is going to be the one end going to the positive terminal of the primary battery. So we're going to connect this up to the positive terminal of the battery. And this is a small 12 volt battery, so that we're not going to push any amps. We're just going to run this we're not going to run it, we're just going to pulse the rotor. And then the other end, and you can do this with just one coil attached, the other two can remain off, and don't worry about tightening it down all the way, because you really have to have all three of these in there and position this just right so that you're not putting too much pressure on the bearings. So you want to make it snug so you can see with it open there's a very slight, there's not actually very much because I still have these on pretty tight, but you have to have, there's a little bit of play there so that you can close it or open it where you want it. So I've got one of these wires here connected to the other end of the coil, and what we want to be doing now is determining when it starts firing in one direction and when it flips over to the other direction. So what we're going to do is, these are north pole, south pole, so you can see the south, north pole facing magnets. So the wires spin, the fields spin this way or the other way, depending on how you pulse it positively or negatively. So if we go, you can see, depending on where it is, it's going to rotate. What I'm doing is putting this to the negative, representing going through the transistor or the FET. So if I was to sit here and hit it at the right time, it would keep spinning. If I hold it down, once it gets to the end of the phase, it's going to reverse, because the next magnet's going to come along the opposite. So it's going to want to spin the other way. So one side's positive, one side's negative, and when it gets to the next phase, then the next coil is the opposite. So anyway, we've already set the timing on this, but what you want to do is, try and do this here so you can see what I'm doing. So what we want to do is look at here. I've set this already. So right now I'm positioned. Let's do it like this so that you can see. So if you can see this right like this, this would be at 0 degrees. And these are 60-degree intervals. So this, at this point, we're really not doing anything. Slightly to the one way we're on here, slightly to here we're off. So we've made these, actually there's a slight off time I think on these. Anyway, so what we want to do is turn these, like, we want to pulse that. We're going to be pulsing this battery until we've come to the place where it doesn't go either way. So let's try that first, and then I'll explain it more. Oops. So I'm right now, let's find this wire. I'm going to be right there. See right there, it's not going to go in any direction because I'm right at the off point. See, if I go a little bit farther over, it wants to go that way. If I'm right here, it wants to go that way. But right in the center, I'm actually off a little bit, so I will want to. So if I'm right here and it's going back and forth, then I have to adjust. I have to adjust it until I get to that center point. So I'll want to fix that so that it's just slightly over, because I don't want it to be counterproductive. In other words, I don't want to be turning the coils on when it's going in the reverse direction. And I have a slight difference here, and so actually my other videos with this running were not as good as they could have been. I guess I need a little bit more light when I'm doing this. Alright, so once we do that, well, first of all, we would have to mount, well, we don't have to mount these yet. Sorry, I'm jumping ahead of here. Once we've set this all up, then with one coil, then we can probably at that point we want to put these in. Actually, we'll probably want to put these in first before we even put them on the plate. So here's plate, and then there would be holes. This one doesn't have it because this is the opposite side. So we want to really put in those optos first, and that way it's not so hard to screw them in. And actually, we can only put in one of them first because you can't put that on with both of them. That's right. So put one on first, put the shaft in and the two sides, then the other one. You can have it one bolt connected, the other one off, and have it loose so that you can flip it around. But otherwise, you can't do that. So it's just a matter of getting the Allen key in there and doing that. So then, after that, of course, we have the keyway, or the keyway on one side here. 2 set screws. This one is on the keyway. You can see sticking out a little bit farther. And then we have 2 on the other side. This gives us some strength to the rotor, but it's a 1/4 inch keyway. It's not going to hold too much torque, like thrust. It's going to be limited. We would have to make another shaft if you want to make this very a lot of thrust, if you want to peel out in your car or something like that. So that is really the basic assembly here. These just come together, come on, it's fairly straightforward. Sometimes we ship this all together because it's easier to ship. Other times we'll send you these coils separately from the rest of the rotor. So that is that. Let's put some of these parts aside. And let's do the electronics. One more thing about this timing hub here. When you are putting the timing pieces on, you only need 1 screw really, because this is not going to come off. But make sure you don't put the timing hub screws on the hole that goes to this hole. So just start off with there or whatever. Alright, these are the bearings. And we like to put the XL Plus lube formula in these. They works really well. So let's move the camera over here now. And look at this. So let's look at the schematic. So not looking at the speed control now, what we're going to look at is just the opto board and the arrangement of the electronics. And we'll go over step by step as we're assembling this today. This represents the timing sensor. Looking at it this way, the legs up. So A, K, E, C, as you can see on the inside there. And then it connects, this is the physical representation of the schematic. So there's a little opto isolator. It's high voltage. So this side of the circuit's 12 volts, which is the timing sensor, and when we add the 555 timer, it's just a 12 volt system, and the rest of it can be high voltage. So from this point on, from this opto isolator, this side of it, and all the transistors or FETs, well, the transistors can be high voltage. The FETs will be low voltage for the gate side. Anyway, so pin number 1 and 2 and this is it represented here with group 1 and group 2, so 2 sets of these. So now we're coming off pin 5 and we're sharing on the collector to either the positive of the primary battery bank powering the motor, or at least 12 volts of it. If you're running 24 volts, you can connect that to 12 volts or 6 volts or 18 volts if you wanted to, if you want to limit the power going to this transistor. And then pin number 4 is going to the base of this Darlington arrangement here. And again, you can see here and here how it's connected. There's the opto, and there's a transistor, an LED on the one side, and just like this is LED triggering a transistor, phototransistor. This does the same thing. So 2 LEDs really. And then from there, this emitter comes out and switches another transistor, which I have here somewhere. Oh, right here. So right now what we're doing is using this transistor, and in this case we're going to have 2. It's going to go to 2 different transistors, here and here, and each one of those is going to go out to either 1, 2, 3, 4, 5, 6 or 3 transistors, or which each go to an individual circuit board, which we have over here. So we have all those transistors right around here. And then we've got this one and this one represented as the first one, as I said. So as this one turns on, it then triggers these gate drivers, as we call them, either group 1 or group 2, and then they in turn turn on all the boards. So then what happens is we can actually just run these transistors directly to the board without these gate drivers. Depends on really what voltage and how many resistors we put. As you can see, we have optional resistors in the circuit. So depending on the voltage and the current being pushed, the transistors need so much to turn on. Unlike the FETs, which is why we're changing them over to FETs here. Anyway, the circuit board, as I said, we have a little socket and a little proto board here, and then we just place these. Don't get mixed up when you are going from one side to the other. It's easy to do that. And what I do is I just bend down the ones that I want to solder on here first. And then I use these I put 3 down. 3 the wires coming across here, and then one goes out like this. So we're going to go and show all this as we get to that point. Just want to do an overview. And we can actually run this first and make sure this is set up right before we do the speed control. Because if we don't do one of them right, we won't know which one it is. It's not easy to figure out how to troubleshoot if you've made one mistake. For example, I spent all night in Germany the other week trying to fix a motor that was broken, and it turned out that one of these had broken, and so it was hard to determine that. I had to replace everything eventually. Anyway, so this represents here a controller, and I think if we do with FETs, then what we're going to do with this particular motor is replace 4 transistors with 1 FET. So we'll have 18 or 18 FETs rather than 72 transistors. And that way we only need, we won't even use boards because there'll be a lot of current. Those boards really won't be able to handle the amount of current that will pass through. And we'll just have to make our own bus bars there. Anyway, we have a heatsink here and a fan connected to distribute the air. And these wires right now are on the outside. They were just for testing. We'll have to bring them through here. So we've got the primary negative terminal with all the black wires, and the charging positive terminal that will come through here. And then on the outside we have this. These are going to connect up to one terminal, which will connect up to the primary positive and the charging negative terminals. And then we want to put a big capacitor across this terminal and this terminal, positive, primary, and then run our wires to the batteries. And then we want to have a switch, a fuse between a slow burning fuse for whatever amperage we're going to be running this up to. We want to have it across the negative terminal of the primary battery. So in there, in line there. And then we'll have various shutoffs, thermal shutoff sensors, which I will bring out at the right time, and we'll connect them up to the heatsink in various places. So what will happen is, if the heatsink, probably put them on top of a transistor, but if the heatsink or the transistor gets hot enough, it will shut off this switch here, and that way it will turn off the opto board and shut down. Now we could also have another switch operating a relay that disconnects the motor entirely, disconnecting the battery, which would be even safer. And could get a latching contactor arrangement where as soon as the heat gets to a certain point, it flips the switch and it turns it off. That way, if anything was happening, like for example, if a transistor shorts out, it may destroy the switch between the collector and the emitter, in which you have a dead short at that point, and it could cause a fire, or it could cause a meltdown of one of the coils. If it was a fire, it would be very minor. There wouldn't be any problem there. If all the transistors went out, which is a rare thing that happens, you would have a bigger problem. But your fuse at that point would kick off. You could put fuses in line with each of the negative wires here. That way, if something goes wrong on one board, it blows out that fuse, which is what we were doing with the one in Germany on the 10 coiler. So you can run that either way. It's your choice how you want to protect it. Fuses, circuit breakers, one way or another. If you're not familiar with working with this stuff, it's really good to have that. That safety is very important. And then just an on and off switch. So once we have this, once we test out one circuit, or actually two circuits, group 1 and group 2, what we want to do is then try the speed control. So we can, as I said, run it without the speed control this way. And the difference will be, in this case, this pin 1 goes to the primary positive terminal, or the 12 volt positive terminal of the little battery powering the optos. This is separate. This can be the primary positive battery, but in this case I have it over here, and we have it isolated. And this is, again, the regular circuit. So now we have that coming to pin number 3 in the 555 timer. And that's all done on this board, so you don't have to worry about figuring this all out. You just have to follow the assembly instructions and then connect up here. And actually the red wire goes into the, well, you can see the little red there. That way we're going to determine the pulse and the width, so the on time or the off time changes in the phase that it's running. So yeah, so the 555 timer has, again, two board that has let's see, a 1M pot and a 50K pot, and you're only going to be using the 50K pot, I think. Once you set up the 1M pot to the right setting, and we'll show that with an oscilloscope. Then, and you don't need an oscilloscope to do this, but I'll show it on an oscilloscope, the difference, what's going on. Then we'll adjust the off time with the other pot. And then we'll make our connections here, 12 volt positive, ground, and then 1, 2, and 3 in these. When you're assembling this board, if it's not already assembled, just be aware that this is number 1 ounce copper, so it's not terribly strong. So once this is set up, What I like to do actually is bring these pots outside of this board and have a bigger pot that I can actually turn as a throttle. And then just sort of enclose this and leave it, crimp it down and not move it. So once we have that done, then we can then adjust the pulsing the way we want it, and just with one circuit first, and then we'll do one board, and then we'll go through each board. The resistance that we use on the base resistors which is represented here, or R1, and all these, that will change depending on what voltage you're going to run this at. So if you're going to run this at 12 or 24 volts, you're going to need to push it harder to get more power. So 10 ohms should be fine. 2 watt 10 ohm resistor is what we provide with the kit. If you're going to go up to 36, 48 volts, you can up that to higher values like 20, 22 ohms. It's kind of relative to, like I said earlier, to how many of these transistors you're running. And if you notice here, this is a bigger diagram, so I'll show this. So, so look at the one side of the circuit, just one group. So as we come off of this transistor, which the collector connects to the primary positive, this transistor here, the collector can either remain open, oops, that collector can either remain open, which I write on the schematic, or it connects to the primary positive, or 6 volts to the, like if you have 12 volt battery, you could connect that to just 6 volts. So if you had 2 6-volt batteries, you could connect it to 6 volt. If you had 24 volts, you could still connect it to 6, 12, 18. You'll find that at some point there'll be too much current and it will actually slow down the motor and it'll produce too much heat in the transistor. And then again, depending on if you have a resistor in line here or here, it's more or less current, more or less voltage. And so these base resistors will vary depending on how high voltage. The higher the voltage, the higher the ohms on your base resistor. So that being said, we're going to run this at 48 volts. We'll start off at 12 and then we'll immediately go into 48 volts and we'll start putting the appropriate resistors in. And I think what we'll probably even do before that is run the FET, run this off of FETs to show that again as part of the video if somebody wants to convert it over to that, or we have that later on, which we may very soon. It'll be both will be in the same video. And then we have on the circuit board itself, we've got diodes here. I have 3 amp diodes on this because I'm going to be running this at 48 volts and I'm not going to be wanting to push this more than 3 amps per transistor, because these are 200 watt devices, and I don't really want to get too close to 200 watts per device. It creates quite a bit of heat, and I want to stay clear of my safe operating area. So I want to, 3 amps is pretty much where I'm going to end off on this. Not to mention, when you are putting a load on this, it is going to draw more amps at startup or under more load, so we want to leave some room for surging and so forth. So 150 watts per device. So 3 amps. I do have 6 and 10 amp and actually 40 amp diodes that could be put in there. These are 1000 volt, and they're not the best, but they work fine. So then, what else do we have? On the circuit board itself, pretty straightforward. We have these terminal strips here, and we bend them, the terminals on the back, 45 degrees, so that we can put them this way as opposed to that way. And then we solder those in, and this allows you to remove the resistors without having to unsolder them. And then you can actually disconnect the wires too for the coils. That way this can be all disconnected one from another. And then what we have here is a heatsink with thermal grease and thermal pads underneath each transistor, and that allows some isolation from the heatsink, so that we don't have a mix between both groups of transistors coming on at opposite phases. So then we'll go over each individual thing. These are just not going to be there actually. And the fan can be hooked up to whatever battery. This is a 12 volt fan. We could use one of our fans from our fan kits too. And then again, this is an on and off switch that just turns these two boards, well, this board on and off. Once the speed control is turned off, there is no power going to the rest of the motor. The gauge wire will depend on how many amps you're pushing in the system. And what I calculated, we're looking at, like I said, 3 amps per transistor here, or in this setup, I'm going to say the maximum amps that we could push in each one of these wires here, I would say heat wise 10 amps each is going to be pretty much the maximum. Otherwise you're going to have to put some extra fan in the motor itself. It shouldn't be too hard to do, or blow air through the motor sideways. So that being said, 10 amps per, I'm not going to push 10 amps per transistor at lower voltage. You could do that with these transistors, but I wouldn't take them that far. But with a FET, if we do 4 FETs, or 1 FET per 4 of these wires, 4 of these circuits, then we're looking at 40 amps per FET at 48 volts. The FETs that I use are 2500 watt FETs, so they'll keep us at about 2000 watts maximum, and that's just with straight on, with no pulsing from the speed control, which is what we won't be doing that full throttle. We'll be breaking it up, and then that is already a 50% duty cycle with the timing there, so long as it is rotating. The only difference with the FETs is if you're going to load this down really hard, then they're going to give you more amps, and so we have to avoid that with this motor. If we use the transistors, that's fine to do that, because you can control the transistors a lot easier than the FETs in that respect. So anyway, so we're looking at 40, let me do some math here. And so if we're looking at if we're looking at 40, so let's see, so 9, yeah, well, if we were to have this, we're looking at while one phase is on, the other one's off, so we have to consider what this will be like in total, the total phase, 360, 9, let's just say 9 FETs times 40 amps, 360 amps would be the maximum that I could probably push this at 48 volts. So we're looking at 17,000 watts, and that includes both sides, averaged out, both phases, group 1 and 2, and that would be about, over 23 horsepower. So then if we were going to do this with the transistors here, 3 times, oops, back here. So we're looking at over 100 amps, it's 48 volts. So, 5,000 watts running this with the transistors. So about 7 horsepower. And that's with full on, not pulsing it. That would be a measurement based upon a conventional motor, which this is more efficient than that, of just using the 700 watt calculation, 746 watts for the horsepower. But this, because it has magnets in it, and because it removes the back EMF and so forth out of the motor, it is a more efficient motor and will be therefore more powerful. So the horsepower will be higher than that. Alright, so let's stop here and start building this. Start off with building this opto board. So what I've done here is I'm going to look at this schematic here. I'm going to place these top hat transistors. This is actually 2N3439, which is virtually the same as the one in here. So if I send you these, you'll know it's the same thing. So notice the little tab on the side here is the closest terminal is the emitter, which is number 3. Number 1's the base in the center, and number 3 is the collector. So the collector is actually a little white, and the other ones are blue. Again, the tab is the emitter. So what I'm going to do is I'm going to leave a space between the two optos. The emitter is going to sit down. You can see the little tab. The emitter is going to be one space below there, and then I'm going to bend that tab out, and these two tabs are going to come and connect up to the socket. Being careful not to solder them together and it's probably best to not solder on the outside of that, because if you want to pull this out, if it blows, then you could remove it easily. This socket you won't have to ever replace. That's why I put it in there, so that we don't have, if we have to replace these, we can. So the same thing with group number, the other group, whatever you're going to call it, group 1 or 2. We want to do the same thing. So we're dealing with the last two. So again, the emitter, I'll leave a space. So it looks like that. We're going to fold these down. And then that's that. Then we want to put a jumper across here and a jumper across here as represented here. So we're going to have positive coming into terminal number 1 and then jumpering across to the other terminal number 1 on the opto. And then on the same thing we're going to do, we're going to have a positive coming into from the collector, going into the collector, another positive wire. But we want to separate those wires because this group right here is representing a different circuit, because this can be an accessory battery. So I always want to separate those two wires. They could be joined if they're all sharing the same battery, but if you want to go later on and change it, you want to have two separate wires coming out. So that's what we did here. So we had one wire going to the collector, and then another wire going there. So then we have two white wires coming in here. The two white wires are represented by these white wires here. The collector of the opto sensor switch is coming off and going to terminal 2 on the opto. So you can see the wire coming into terminal 2 there, and then the other wire from the other sensor coming into terminal 2 there. On the other side, we've got these two wires, a green and a white wire, and those are represented the E emitter terminal here. From there is going to be group 1 will be one color, and group 2 will be, one will be white, one will be green, or whatever color you want to use. But I have them here. So these wires are going onto the heatsink because I want to mount this transistor on a heatsink. It may not get that hot, but I like to have these transistors on heatsinks. So I have them right here as this transistor and this transistor. And then from there, these are going to be going to all these base terminals of these gate drivers if we're going to use those. As I said, now these center terminals are the collectors again, and they may or may not be connected to the primary positive. So we're going to just use the base and the emitter terminals on those transistors most of the time. If we're going to get into higher voltage especially, we don't need them. So then we've got that together, we've got to put our wires in, and then what I'll do is I'll put on this one, we have already, these are the wires coming represented here, here and here. So across the negative we can put a switch, which is what I've done right here. And then we can connect that to a fan. The fan, if we want the fan connected to that battery as well. Or we can just, you could just use a little tiny battery because it's not going to take very much power to run those LEDs in the 555 timer. And then we'll hook this all up together and we'll go one stage at a time. I think that's good for now.